Hello everyone, and welcome to a new series about the causes of high pore pressure. Today we'll explore one of the important mechanisms behind abnormal pore pressure, gas generation. Let's first understand the equation that governs the relationship between gas volume and pressure. This is the ideal gas law, PV equals nRT. It describes the relationship between gas pressure, volume, the amount of gas, and temperature. P represents pressure, V is the gas volume, N is the amount of gas in moles, R is the universal gas constant, and T is the absolute temperature in Kelvin. From the equation, we can see that pressure is directly proportional to the amount of gas and temperature, and inversely proportional to the available volume. In other words, increasing the amount of gas or increasing the temperature tends to increase pressure, while increasing the available volume tends to decrease pressure. Now, let's connect this concept to petroleum geomechanics and see how gas generation can contribute to high pore pressure, particularly in organic-rich source rocks during hydrocarbon generation and maturation. The basic mechanism is, when kerogen matures, hydrocarbons are generated. During the oil-to-gas and gas generation stages, a significant amount of gas can be generated within a relatively low permeability source rock. If the generated fluids cannot escape efficiently, the pore fluid pressure increases. Organic matter maturation leads to hydrocarbon generation, leads to oil, leads to gas generation, leads to volume increase, leads to pressure increase. Gas is much more compressible than formation water, but gas generation can introduce a large hydrocarbon volume into a confined pore system. If the source rock has very low permeability, the generated fluids may become trapped. This can lead to increase in fluid volume, increase in pore pressure, reduction in effective stress, undercompaction and/or hydraulic fracturing, development of natural fractures or microfractures, migration of gas into adjacent formations, possible development of a gas chimney. Gas generation by itself does not automatically mean high pore pressure. The critical condition is gas generation plus restricted fluid escape plus sufficient confinement equals potential abnormal pore pressure. This is why rapidly generating hydrocarbons in a low permeability, overpressure source rock can contribute to abnormal pressure. You can describe the mechanism as rapid burial/maturation to hydrocarbon generation, to gas generation, to fluid expansion, to pressure buildup, to reduced effective stress, to abnormal pore pressure. You can describe the mechanism as rapid burial/maturation leads to hydrocarbon generation, leads to gas generation, leads to fluid expansion, leads to pressure buildup, leads to reduced effective stress, leads to abnormal pore pressure. And if the pressure becomes sufficiently high, high PP leads to reduced effective stress, leads to failure/fracturing, leads to fluid migration. This is one of the mechanisms I would include alongside compaction disequilibrium and aquathermal/chemical mechanisms when explaining the sources of abnormal pore pressure. Now, let's look at the pore pressure profile in a reservoir containing water, oil, and gas. The first important point is that the pressure gradient is different for each fluid. Water has the highest pressure gradient. Oil has an intermediate gradient, while gas has the lowest gradient because of its much lower density. However, a low gas pressure gradient does not necessarily mean low pore pressure. If gas generation, fluid expansion, and restricted fluid escape cause the reservoir to become overpressured, the gas pore pressure can be significantly higher than the normal hydrostatic pressure at the same depth. As pore pressure increases, effective stress decreases according to the relationship between total stress and pore pressure. If the pore pressure becomes sufficiently high to overcome the minimum principal stress and the tensile strength of the rock, fractures can initiate. These fractures then provide pathways for the gas to migrate upward through the overlying formations. Continuous gas migration can eventually develop what we call a gas chimney. So, the key concept is not simply that gas pressure must be higher than water pressure. The critical point is that hydrocarbon generation can elevate pore pressure above the normal hydrostatic trend, reduce effective stress, and eventually trigger fracturing and upward gas migration. That's all for today. If you enjoyed this session, don't forget to like, share, and subscribe. See you in the next one. On behalf of the Geo Insights consultancy team, we encourage you to follow our YouTube channel and LinkedIn page to stay updated and never miss any of our new content.